Hey guys! So right now we're going to be going over how to do the calculations for the molar volume of a gas Vernier lab that we recently did. This pre-lab or background information explains a lot of information, so I highly recommend rereading it before you go on to do the calculations. It will actually tell you how to calculate the number of moles from the balanced reaction. As you see right here, 1 mole of magnesium produces 1 mole of hydrogen gas. Knowing the mass of magnesium will determine the moles of hydrogen gas produced, and then we'll confirm Avogadro's hypothesis using the combined gas law to calculate the volume at STP of the hydrogen gas our reaction produced, even though our reaction was not at standard conditions, or STP. So let's go ahead and look at some example data. So here's my example data for one trial. I have my mass of magnesium, the volume of my flask, the maximum pressure that I reached after the reaction had completed, the initial pressure, the pressure before the reaction started, the change in pressure, and the temperature. And note, I converted the temperature to Kelvin because whenever we're doing combined gas law or any type of gas law calculations, we want to be in Kelvin. Okay. I also want to talk about the pressure change. This pressure change is due only to the hydrogen gas that's being created. There's no other gas being produced, so this you can think of as the partial pressure of the hydrogen. Okay, so when doing the analysis, the first step is to calculate the molar amount of the magnesium. That's just converting from the grams of magnesium that we used to the moles. So I'm going to label my calculations and start with just trial 1. I have 0.012 grams of magnesium, and in order to convert from grams to moles, we of course use the molar mass. The molar mass of magnesium is 24.31 grams per each 1 mole. Okay, so we plug that into our calculator, 0.012 divided by 24.31, and we get 4.94 times 10 to the negative 4. You might also not have it in scientific notation if it's just in normal. Okay. You will get it like that. I personally prefer scientific notation, so I'm going to keep it like that. But either way that you do it is fine. Okay, so I have 4.936. I want to round it to 3. I'm missing a sig fig there, but I'll round it to 2 sig figs since I only had 2 sig figs there. So I have 4.9 times 10 to the negative 4 moles of magnesium. Okay, that's how many moles I reacted in my flask. Now, calculate the amount of hydrogen gas that was produced. 1 mole of magnesium gives 1 mole of hydrogen gas. It's a 1-to-1 ratio, so this means that my moles of hydrogen gas produced is also 4.9 times 10 to the negative 4 moles of magnesium. Okay, you can think of it like this: 1 mole of magnesium equals 1 mole of hydrogen gas, using the mole ratio from the balanced chemical equation. Okay, the next step is the hard one. This is where you're going to calculate the volume of 1 mole of hydrogen gas, the molar volume, at STP. So our conditions were not standard. Standard temperature is 273 Kelvin. We weren't there. Standard pressure is 101.3 kPa, and we're not there either. Okay, so I'm going to have to use the combined gas law. Okay, so let me list my variables first. In my experiment, my pressure of the hydrogen gas was 8.1 kPa. Standard pressure, the one that I want to know, is 1 atmosphere, which is 101.3 kPa. The volume that my hydrogen gas was at is equal to the volume of the flask, which is 146 milliliters. I know later I'm going to have to work in liters, so I'm just going to go ahead and convert that right now. My volume was 146 milliliters, which is equal to 0.146 liters, okay? It's just moving the decimal over 3 times, or you can think of it as dividing by 1,000. My volume of the hydrogen gas at STP is what I'm looking for, okay? So that is going to be my unknown. The temperature that I was at was 296 Kelvin. Standard temperature, so T2, is 0 degrees Celsius, which is 273 Kelvin. Okay, so now I'm ready to plug and chug and find my volume 2. Okay, remember the ideal gas law is P1 V1 over T1 equals P2 V2 over T2. Okay, so my pressure 1 is 8.1 kPa times my volume 1, 0.146 liters, over my T1, which is 296 Kelvin. Okay, that equals P2, which is 101.3 kPa, times V2, that's what I'm trying to find, times 273 Kelvin. Okay. Easiest way, I'm going to multiply this all together and then multiply it by 273. So I have 8.1 times 0.146 divided by 296. So I got 3.9 times 10 to the negative 3. And then I know I'm going to times that by 273, so I'm just going to do that right now. Times 273. So right now I'm at 1.09 equals 101.3 kPa times V2. Divide each side by 101.3. And I get a V2 of 1.076 times 10 to the negative 2 liters. Okay, so in just regular terms, it's 0.01. I'm going to keep it at 2 sig figs, so I'm going to say 0.11 liters. Okay, so you might be tempted to stop there, but remember, this is the liters for that much hydrogen gas. Oops. That should be hydrogen gas. Okay, for that many moles of hydrogen gas. I want to know the volume of 1 mole. Okay, I'm trying to compare it to 22.4 liters per mole. So I have 0.011 liters per that many moles. To get my liters per 1 mole, I just divide it. So 0.011 liters, that's my V2. Okay, I'm going to divide it by the number of moles. 4.9 times 10 to the negative 4 moles of H2. And that will give me how many liters 1 mole would be. So 0.011 times, divided by 4.9 times 10 to the negative 4. Enter, and I get 2.2 times 10 to the 1, aka 22.4 liters. And, because this is sample data, it matches up exactly. Isn't that awesome? Okay. Odds are you're going to get somewhere in between, hopefully between 18 and 25. But once you have this for all 3 trials, you can take the average of them and compare what you calculated to the accepted value, which is 22.4. If they don't compare very well, suggest possible sources of error. Maybe you know that you did something wrong during the experiment, some of the gas was escaping or anything like that. That will help you out. Okay, but to refer back, let's go over what we did. I'm going to grab another piece of paper, pencil to annotate it. Okay, first we converted to moles. Come on, pen, work. First, we converted 2 moles. Okay. Then we found our moles of H2 from our moles of magnesium. Then we used the combined gas law to see what the volume would be at STP. So find volume of our gas at STP, okay, using the combined gas law. Then we divided it out to get the molar volume, okay, aka the volume of 1 mole, not just of 4.94 times 10 to the other thing. If you wanted to, you could even do a version of the combined gas law that has N in it, which is the number of moles. Again, this all comes from PV equals nRT. If you just solve for R, it's PV over NT. And if you do R amount of moles in 1 and 1 in the 2, it will also work out well. Any way you do the calculation is fine. Just make sure that you are making sense, okay? So this is how many liters per mole our gas had. Okay, cool? Okay, cool.